Hello everyone, and I hope you're doing well. Today I will be going over Lewis structures for organic chemistry, which will kind of include a general review of Lewis structures from any general chemistry classes you may have taken. I'll go over a little bit about orbital hybridization, and I will talk about resonance structures and how we as organic chemists will be writing our Lewis structures out in a slightly different way from what you may have seen in general chemistry. So let's start with the basics. So let's start with Lewis structures and bonding and how the electrons will sort of interact with that. So the idea with atoms here, so let's take oxygen for example. So oxygen, right here's our oxygen, our beautiful oxygen. So when we look at our periodic table, we can tell how many electrons total it has, which is generally going to match the number of protons, which is going to be our atomic number. So oxygen in total has 8 electrons. However, when we are talking about Lewis structures and bonding and all of that stuff, generally we'll be looking for something called our valence electrons. These are our electrons that are on the outer shell of our atom. So the idea here is that every single atom is going to be surrounded by different shells of electrons. The first shell, for example, will hold 2 electrons, and then most shells after that will hold up to 8. So in this case, we have 8 electrons total. So when we draw in our electrons in our electron shell, 2 will go in the first orbital, and then the rest, which will be 6, will go in the outer valence orbital. Now, of course, you could do this process over and over and over to figure out how many electrons are in our valence shell. In this case, with oxygen, it is 6. Or you could go to the periodic table and you can say, okay, looking at my noble gases are generally unreactive, and this is because they will generally have 8 electrons in their outer valence shell. And because our outer valence shell can only hold up to 8 electrons, they are not likely to form a new bond to make to add more electrons to its valence shell. However, as we move to the left like this, we can say that we will go down in valence electrons as we move to the left. So our noble gases will have 8 electrons. Our row here of halogens, which is fluorine, chlorine, bromine, iodine, etc., they will have 7 valence electrons. This row here with oxygen will have 6. Nitrogen, 5, carbon 4, boron 3, beryllium 2, hydrogen, lithium 1. So in this way, it's a really fast and quick rule of thumb to figure out how many valence electrons that we have without going through this whole process right here. And so why are we interested in valence electrons? So the valence electrons are the only electrons within our atom that will be able to form bonds. So for example, if we're looking at oxygen here, only the 6 electrons on the outside will be able to form bonds with other atoms. Our electrons within that inner shell, that non-valence shell, will generally not be able to form bonds. So let's take our oxygen example and let's draw it in its valence or in its Lewis structure form. So instead of drawing everything out, because that would take a little while, instead what we're going to do is we're just going to go ahead and draw our O as our representation of our element, and then we're going to go ahead and just draw in 6 electrons around the oxygen. And what you'll notice is you'll see me generally drawing them in pairs because electrons show up in pairs. However, it would not be incorrect to draw it sort of like this, where there is, instead of having 3 pairs, we have two pairs and then 2 lone electrons. Both of these should be okay because what you'll see is that 2 of these electrons are going to participate in further bonding. But this is just sort of how we draw oxygen in its base Lewis structure form. So now let's talk about something like H2O. So instead of just oxygen, we have oxygen that is bound to 2 hydrogens, indicated by H2. So we know that they're going to be bound to hydrogens, so we're going to go ahead and represent that with just a line. Oops. And so each line is going to represent 2 electrons. And in this case, 1 will come from the oxygen for each bond, and then 1 will come from the hydrogen from each bond. And so if we look up at our periodic table up here, what we'll see is hydrogen will tend to have 1 valence electron, and oxygen will have 6 valence electrons. So what will happen is that the lone electron from a hydrogen will pair with one of the lone electrons of the oxygen, and the same will happen with the second hydrogen, with the other 2 electron pairs just being right here. Okay. So what we'll see in Lewis structures is we will see a big letter as a representation of our atom, and we will see bonds in the form of lines, which will make up 2 electrons, and we will see electron pairs in the form of 2 dots. One more thing to note is that, let's say, for example, instead of having H2O, we have something like CHO. And I'll explain how I know the structure of this in a little bit, but first, I will know the structure of CHO to be a carbon bound to an oxygen, bound to a hydrogen. Actually, let's say this, CH2O. So I know it's going to look like this. So something to note is that when we have 2 lines, that's going to represent a double bond, and if we have 3 lines, that will represent a triple bond. Each one of those lines will contain 2 electrons. So in this case, oxygen will again have 4 electrons in 2 pairs, and then it will have a double bond with carbon, so it's sharing 2 electrons with carbon, and carbon is sharing 2 electrons with the oxygen. All right, so how do I know that this is going to be the structure of CH2O? How do I know that? Well, it's a little complicated, but it's a little complicated, but once you break it down, it becomes a lot easier to understand. So let me go ahead and clear this a little bit. All right. So the idea here is all of this is going to have to do with our valence electrons. So like we said, oxygen will have 6 valence electrons. And if we look here, we know that carbon will have 4 valence electrons. The number of sort of available positions in that outer valence shell will help inform us of how many bonds it can make. So for example, oxygen, because again, our valence shell will hold 8 electrons, oxygen wants 2 electrons to fill that valence shell, so it's going to generally be able to make 2 bonds. With carbon, same thing. It's going to have 4 electrons in its valence shell. It's going to want 4 more electrons to make a full valence electron shell, so it's generally going to make 4 bonds. Of course, there are exceptions to this rule, as there always are, but we'll get to those in a little bit. So if we continue, if we looked at, and finally hydrogen, 1 electron, and because hydrogen, it only has 1 electron shell, and we know that the most inner electron shell will hold 2 electrons. So instead of holding 7 extra bonds, hydrogen will generally only hold 1 extra bond to fill that inner valence shell. So if I looked at our CH2 oxygen, or CH2O, we know that these hydrogens, they will want 2 bonds total. This carbon will generally make 4 bonds, and thus oxygen will also make 2 bonds. And I said the hydrogens will make 2 bonds because there are 2 of them. Each one of them will make 1 bond, so in total they will make 2 bonds. And if we compare these, and we're saying, okay, so this whole thing is going to be 1 singular molecule, that means everything has to be linked up in some way. So for example, let's say that instead of drawing this conclusion, we were trying to say, okay, well, what if instead of carbon being the central atom, we said oxygen was the central atom? Then we could have it bound to a carbon right here, And if we wanted to go ahead and bind it to a hydrogen right here, and we said, all right, there we go. There is our two bonds for carbon, our two bonds for oxygen rather. And we say, okay, the last hydrogen can go onto that carbon. That carbon is going to be relatively unstable now because instead of having 4 bonds to fill up its valence electrons, it's only going to have 2 bonds. As a result, it is going to have only 2 electrons added to it. So it's going to sort of end up having 2 valence electrons on it. I hope that makes sense. And generally, when we are drawing the structures here, we are going to want to draw the most stable structure because in nature, that's sort of how things will sort out. Generally, what will happen is that things will form the most stable version of itself. When you sort of throw, I don't know, a three-sided dice onto the is that three-sided? No, 1, 2, 3, 4. A 5-sided dice or whatever sided dice this is onto a table, it's not going to sort of land with its tip on the flat of the table because that is generally unstable. It's going to fall over and be on one of its flat sides because that is stable. That's the same idea here. While hypothetically this could happen, it could land right on the point on the flat of the table. That's not really going to occur as a general rule of things. So this is what we are going to end up be drawing here. All right. So the next thing to talk about is something called formal charge. So the idea here is that, so let's say that we had that structure, that kind of weird structure that I drew where I have carbon here attached to an oxygen here with a hydrogen here and a hydrogen here. Again, you're generally not going to see this because it is pretty unstable, but you might be asking, okay, I understand that the valence electrons, we generally want to fill those, and so that's why this is unstable. But how can I know that when I'm looking just at a structure here? Well, what we can do is we can look at something called the the formal charge rather. The formal charge. So the formal charge in a Lewis structure is going to be the localized charge upon one singular atom. This is different from something called the net charge. The net charge is going to be sort of the overall charge of the whole molecule. Most of the time, our net charge is going to be all of the formal charges added together. So how do we figure out this formal charge? So thankfully, there is a pretty easy mathematical formula that we can use for it. And that mathematical formula is going to be the number of valence electrons in our regular atom. So in this case, for carbon, that would be 4, minus the number of bonds. You could also say the number of electrons in bonds, and you can think of it as, well, each atom is sharing a bond, so they're sharing those electrons. So even though each bond has 2 full electrons, only one of those is going to, quote unquote, be owned by our atom that we're looking at. So in the case of this carbon, we have 2 bonds. And finally, we're going to subtract the number of electrons in lone pairs. So up here, I didn't exactly draw it as a lone pair, but what we would see in nature is that those 2 atoms would sort of end up pairing, or those 2 electrons would end up pairing up. And so we know we have two electrons in one lone pair. All right. So in this case, this carbon does have a formal charge of 0. However, if we went ahead and filled up that valence, those valence spots, so we give our carbon the full 8 electrons, what we'll see is we end up with, minus 4 here, we end up with a charge of -2. So our formal charge of this carbon with a full valence shell will be our -2. All right, so if we go ahead and we calculate all of the other valence charges, you'll see that all of these will have a valence or a formal charge of 0. So what will happen is our net charge will end up being -2. All right, so this is going to, so both the valence electron shell and our formal charge is going to sort of help inform us about the state of our atom, the state of our molecule, our Lewis structure in general. It's going to tell us a lot about the stability and which of the possible formations of a molecule might form. All right, so let me go ahead and erase all this. All right. So you may be wondering, okay, so what does this have to do with organic chemistry? I've seen those drawings in organic chemistry books. They look nothing like Lewis structures. So the idea in organic chemistry is we're dealing with a lot of carbon chains. So let's say that we had like a 4-carbon chain and it had all of its bonds filled. Each carbon had 4 bonds. So we're going to say we have a 4-carbon chain right here. And then every one of its other bonds is going to be filled in with a hydrogen. And the reason why I'm filling it with hydrogen is because in nature, that's generally what happens with a carbon. If it's not, if some of its bonds are not filled up by another atom, it might grab a hydrogen. And what you'll notice here is that every one of these carbons will have 4 bonds. If we do our formal charge calculation here, carbon has 4 valence electrons in its normal state, minus 4 bonds, minus 0 electrons in lone pairs, it is going to be neutral. And atoms like to be neutral, so this is going to be an overall very stable molecule. Okay, so let's say instead of 4 carbons, I had 20 carbons. Drawing that Lewis structure, drawing this structure over and over and over and over is going to be pretty tedious. So organic chemists, some people in the past decided sort of a shortcut for that. So instead of drawing the full Lewis structure, what we're going to do is we're going to draw a series of sort of zigzag lines. The rule here is that every single point, so either end or kind of triangle point here, that is going to be a carbon. And unless otherwise specified with something like a formal charge of a negative or a positive charge, or the presence of another bond, another atom, so like for example, if one of these carbons were bounded to oxygen, all of the remaining bonds will be filled in with hydrogen. However, that will not be drawn in this case. It is implied. So whenever you're looking at a carbon chain like this, you need to make sure to think that our hydrogens, they're not drawn in, but they are implied, because I would break my wrist if I tried to draw every single hydrogen on something like a 20 carbon chain. So the idea here, so let me go ahead and draw an example. So let me get this. This is just going to be off the top of my head. So let's say that we've got this right here. So like I said, every single one of these points is going to be a carbon. So if I were to draw the Lewis structure here, I would say, okay, there are 4 carbons here. I know that this carbon is double bonded to an oxygen. And I also know that now that this carbon is double bonded to an oxygen, it has 8 valence electrons in the form of 4 bonds. So it's happy, it's not going to want to form any other bonds, and in fact, it really can't, because once an atom sort of fills its valence shell and it does not have any other empty shells, it can't really form more than 4 bonds. There are exceptions to this, and I'll go over that in a second. But the idea here is now we're looking at the other carbons. We can look at each of these carbons in sort of our modified Lewis structure here, and we can see that they all have a 0 formal charge. And when a carbon has a 0 formal charge, generally it's going to have 4 bonds. So if I look at each carbon, I can see that this carbon right here has 1 bond. As a result, it's going to have its remaining 3 bonds filled in with hydrogen. This carbon right here has 2 bonds. Its remaining 2 bonds will be filled with hydrogen. And the same state right here with this carbon with a single bond. So as you can see, it took me a lot longer to draw the Lewis structure than it did to take me to draw this alternative form of our Lewis structure here. And so that's the reason behind why we do that. All right, awesome. So you heard me talk about how some electrons can sort of violate the octet rule, and it's going to have more than 8 electrons around it. It's going to have more than a valence shell will allow. So the idea here will be with sulfur. So sulfur is probably the most common that you'll see, and you'll generally see this with something like H2SO4. So the Lewis structure for H2SO4 is going to look like this. And oh, sorry, let me draw the full Lewis structure. I'm too used to drawing the sort of truncated version. But what we'll see here is we'll see 2 sulfur bonds to single bonds to oxygen with a hydrogen attached to the oxygen. But then we're going to see 2 double bonds between sulfur and oxygen. And you may go, wait a minute, and you count all these electrons up, and you say, sulfur has 2, 4, 6, 8, 10, 12 electrons. That violates our octet rule. But the idea here, it has to do with something called our orbitals. I know I mentioned that a minute ago, where we have our sort of our simplistic overview right here, where we have our circles around our S. But the idea here is that these orbitals, they're going to have sort of specific names. So the first 2 electrons, they will go into something called the 1s orbital. And then the next 2 electrons will go in the 2s. So 1s will hold 2, 2s will hold 2, and then something called T2p can hold up to 6. And so what you'll notice here is that 2 and 6 are 8. So these 2 orbitals make up this outer ring. It may be confusing, but it's okay because orbitals don't play a huge role in organic chemistry. But what they do play a role in is something called hybrid orbitals, as well as making something violate the octet rule. So as we go down, we continue following this pattern of S then P, S then P, S then P, but then we get something called the d orbital. That is not a D, the d orbital. So the d orbital has to do with sort of our transition metals right here. And so if you look here, there is sort of like a missing row right here, where there are no atoms because they don't exist in the periodic table there. But you can see here that something like sulfur is still within that row. We can say then that the sulfur will have an empty d orbital, and as a result, it can sort of store extra electrons in that empty d orbital. And so as a result, our sulfur can have more than our standard 8 electrons and violate our octet rule. All right, so let's go over some sort of general rules with Lewis structure stability. So they will follow the octet rule, which generally means that every atom is going to want 8 electrons total around it. We're going to want our formal charge to be as neutral as possible. So I'm going to say formal neutral. Of course, we can't always have a full neutral charge, so there are a few rules that have to do with this. So I want it to be as neutral as possible. So for example, a -1 charge is more neutral than a -2 charge. Resultingly, our molecule is going to prefer having the -1 charge. Also, something to note is that if you have to have a negative charge, you're going to want that negative charge to go on an electronegative atom. So that electronegative atom, that name is sort of exactly what it says. The more electronegative it is, the more likely, the better it handles a negative charge. And if you recall from general chemistry, the general pattern is that as we go up into the right on our periodic table, the more electronegative we will be. So for example, fluorine is more electronegative than oxygen, which is more electronegative than nitrogen, which is more electronegative than carbon. So the idea here is that oxygen will hold a negative charge much better than a carbon. So overall, if we have to have a negative charge on our Lewis structure, we're going to want to put it on an electronegative atom like oxygen. And the same is the opposite, the opposite is true for a positive charge generally. Generally, we want to be less electronegative for a positive charge. So for example, carbon will handle a positive charge better than an oxygen, but this rule is less set in stone than our electronegative rule, so you may see some bending of the rules here and there. All right, so let's look at a possible Lewis structure. So let's say that we have this here, and let's say that instead of having a hydrogen on this side, this carbon has a lone pair. When I go to calculate this lone pair, or calculate the formal charge on this carbon, I'll say 4 valence electrons minus 3 bonds minus 2 electrons in lone pairs, I get a charge of -1. So I'm also going to check that my carbon fulfills the octet rule, meaning it has 8 electrons. It does, so we're good. So now we're looking at this carbon and we're saying it has a negative charge. And when we check the valence or the formal charge of all of our other atoms here, we will go ahead and see that, that they will be all neutrally charged. Okay, let's say that instead of having no bond over here, this carbon will actually have an oxygen over here. This oxygen will have 3 lone pairs and no double bond with carbon, because if it made a double bond with carbon, that carbon would have 10 electrons, which violates the octet rule. So let's go ahead and calculate the formal charge on that oxygen. Oxygen will start out with 6 valence electrons minus 1 bond minus 6 electrons in lone pairs. Therefore, we end up with an overall charge of -1. However, keen-eyed observers among you may have noticed that I can draw this Lewis structure in a different way, where instead of having the negative charge on this oxygen, let's call this oxygen A and we'll call this one oxygen B. Instead of having the negative charge on oxygen A, it can actually go on oxygen B. So all we've done here is we sort of switch the positions, or we switch the bonding environments of oxygen A and oxygen B. And both of these are valid. And they are something we will call resonant structures of each other. So I'm going to put resonance down here. Now, resonance is a topic that a lot of people have issues with, but the general idea is that every single bond here is going to stay the same. So we have the same base structure of our molecule. However, what can change are the positions of double bonds and the position of lone pairs. Because what you'll see here is essentially what occurred is that this double bond right there, it broke and then was put on this oxygen as a lone pair. And the opposite happened on oxygen A, where the lone pair on oxygen A made a double bond with carbon. So what you'll see here is that we're moving either double or triple bonds, or we're moving lone pairs. So what we'll call these bonds right here, these extra bonds, we're going to call those pi bonds. And then those base single bonds will be sigma bonds. And you'll see these with the pi symbol and the sigma symbol. So what does this mean? That means that every single bond will be made up of a sigma bond, and any other extra bonds on top of that will be a pi bond. So for example, if we have a triple bond right here, this will be made of 1 sigma and 2 pi bonds, where the sigma is going to be that base right here, and then the pi bonds are going to be whatever is extra. So when we talk about resonance, what we'll be talking about is the movement of electrons, but our constitution, the base structure, will remain exactly the same. So let's look at some more examples of this. So I'll erase this. And again, resonance is a hard topic to understand, so it's okay if it doesn't make complete sense yet. So let's do a very, very simple resonance. So let's say we have a carbon triple bond to an oxygen, and actually let's do ozone. So ozone is O3, and it's kind of like our poster child for resonance. If you talked about resonance, you probably talked about O3. So the idea with O3 is that each one of these oxygens will have 6 valence electrons. So that means we have sort of 18 electrons total to play with. So that means there are only a few configurations we can make. One of those configurations looks like this, and the other configuration looks like this. Oops. Like this. So again, what you'll see here is that we see we see lone pairs and we see double bonds kind of moving around. And so what I'm going to do here is I'm going to show you the movement of those electrons with something called a mechanism arrow. Basically, mechanism arrows are going to show the movement of electrons. So for example, we can see that this bond moved and became the lone pair on this oxygen. On the other side, we can see that a lone pair, it could be any of them, but I'm just going to choose this one, became a new double bond right here on this resonance structure. So what we'll see here is that in our resonance structures, when we want to show the movement of electrons, we're going to use a double-headed arrow because double-headed arrows show the movement of pairs of electrons. And you can think of this as each sort of barb of the arrow holds one electron. On the other hand, if we have a half-headed arrow, that will show the electron movement of a single electron. I won't be using single barbed arrows in this lesson here, but I thought it'd be important to note. All right. So given these two, and then let's go ahead and write in the formal charges. This middle oxygen, for both of them, has 6 valence electrons, minus 3 bonds, 1 double, 1 single, minus 2 electrons in lone pairs. So in both cases, this oxygen will be positively charged. On the other hand, we can see that this oxygen right here and this oxygen right here, they'll have the same sort of formal charge equation here. 6 valence electrons minus 1 bond minus 6 electrons in lone pairs, that equals -1. So both of these will end up being -1 formal charge. So our net charge for ozone is 0 because the negative and the positive cancel out and we end up with an overall charge of 0. However, we're still looking at the formal charges here because later they will help us understand how reactions occur. But right now, just understand the concept. All right. So we have our two resonance structures here. And if I were to ask you which one of these is what actually occurs in nature, that would be a trick question. Because what actually is seen in nature is something called a hybrid resonance structure, where each resonance structure, that is not resonance, I can't spell it very well, where each resonance structure is going to contribute to the actual structure in real life. So the way that we would draw this is we would draw like a box or 2 brackets right here. I would draw the base form. So in this case, all of the sigma bonds are there. And I know that in both of these resonance structures, this oxygen is exactly the same. So I'll go ahead and draw that in. So what we see in a hybrid resonance structure is that these resonance structures are sort of swapping so fast between each other. What's going to occur is we're not going to see one or the other full structure in nature. Instead, what we'll see is we'll see a partial bond wherever there is a double bond. And we'll represent that with our dotted lines here. And then what we'll also see is we're going to see partial negative charges wherever there would be a full negative charge. And the reason for that is if we try to do our formal charge equation, so 6 minus, well, how many bonds do we have? Well, we have at least 1, but then we have a partial bond right here. So how many bonds do we, so in that way, we can't fully calculate the formal charge, but we can see that, well, it's at least going to have some negative charge, and that's what that symbol means, partial negative charge. Something else that you'll note is that in a lot of times in our hybrid resonance structures, we will not draw in our electrons. And the reason for that is because we don't know what electrons are participating in this partial bond. We can't have a partial electron. We can't have half an electron on our oxygen, half our electron in our double bond. So what you'll see a lot is they're sort of not drawn in, but rather implied, a lot like we saw hydrogens being implied in our alternative Lewis structure for organic chemistry. And so that's generally how resonance will work. Of course, this will come into play a little bit later when we talk more about stability and acid-base stuff. But for right now, just get to know resonance, become best friends with resonance because it's very, very important. Okay, so the last thing I'm going to talk about today are something called hybrid orbitals. So hybrid orbitals, they're really, really fun. They're very, very important. However, for organic chemistry, the only big portion of hybrid orbitals we are going to use are going to be our sp hybrid orbitals. So just like I said before, I said previously in this lesson that when we have our electrons, they're going to sort of fill out in a very, very specific way. And this has something to do with something called the Aufbau principle, Pauli's pairing, etc. But I'm just going to teach you the basics. So the idea here is that each electron can be in an energy state. The S energy state is going to be the lower energy state. The P energy state is going to be the higher energy state. And something else to note is that each one of these lines here can hold 2 electrons. So if you remember, S can hold 2 electrons and P can hold a total of 6. You may be wondering why I'm drawing electrons like this. Well, it's because whenever we see electrons in pairs, one will be spin up and one will be spin down. And as a result, that's how we're going to go ahead and represent it in these graphical representations. All right, so this is great. This is beautiful. This is an amazing, this, for example, if we're looking at S2 and P2, this would be our neon valence electron structure. However, let's look at something like oxygen. Oxygen is who I'm using a lot today. So if we're looking at oxygen, we have our s orbital right here, and then we have our 3 p's right here. So what's going to occur is oxygen has 6 electrons. And so what we'll do is we'll have 2 electrons in s, because if you think about it, why would our electrons walk up these stairs if it could just get in on the ground floor and just sit right there? As a result, the s orbital will end up being completely filled, which means that instead of having 6 electrons, we now have 4 electrons to fill with our p orbitals. Something else to note is that they're going to fill in 1 p at a time. Because you can think about it, it's much better to have no roommates than a roommate if you like living alone, and these electrons do. So that gets rid of 3, so we're left with 1, which we'll go ahead and fill in right here. Now, when hybridization occurs, what's going to happen is that the s and one or more of our p orbitals is going to kind of meet in the middle. And as a result, we're going to end up with something kind of in the middle of the energy spectrum, neither S nor P. So we're going to call this either SP1, SP2, or SP3, which depends on how many p orbitals are interacting to create these hybrid orbitals. And of course, it's going to depend on the bonding of our atom. Okay, this feels really complicated so far, but generally the idea here is electrons like to be in low energy positions. P orbitals are higher energy positions than s orbitals. So what's going to happen is that sometimes the s will feel bad for the p, they will meet in the middle, and they will make an sp hybrid orbital. Neither an s nor p, just something in the middle. If you're very, if you love talking about the geometry of orbitals, then you'll see that it'll meet somewhere in the middle. Neither a spheric S or this shape P. It's going to be sort of like a distended P kind of thing. If you're not interested in geometry, don't worry about it too much. So again, the whole point of these sp orbitals is to make something a little bit more low energy for the electrons. So now let's go ahead and talk about carbon. I'm going to go ahead and erase this just so we have a little bit more room. So let's look at our lovely friend carbon, which we will be best friends with during organic chemistry. So carbon, if I go ahead and draw our energy diagram here, is going to have 4 electrons. So it will have 2 in S, and then it will have 2 in P. All right. So let's say that our carbon is going to decide to make 4 bonds with hydrogen. So the idea here is if we were just doing this straight up, we were just looking at this and we were just filling this in with our electrons from our hydrogen, what we would see is we would see something like this. However, if we look here, we would see, well, hydrogen can't really pair an electron with itself. As a result, what's going to happen is these p orbitals in this s orbital, they're going to kind of get mixed up. And instead of having 1 s and 3 p, we're going to have 4 sp3 orbitals, neither s nor p, somewhere in the middle. And what's going to happen here is that the carbon is going to give one of its electrons to each of this sp3, and then the hydrogen s will then go ahead and fill in the rest of that orbital. Right, I hope that makes sense. So in this case, this carbon here, this carbon will have an sp3 hybridized orbital, and all these hydrogens, they will still be 1s. So if there was a question about, let's say that what orbitals make up this bond, the answer would be a CsP3 orbital and a hydrogen 1s orbital. All right, so I've made it very simple there, but let's make it more complicated because organic chemistry in general likes to be complicated. So let's say that instead of that carbon, we have instead a carbon with a double bond to an oxygen, a hydrogen, and a hydrogen. So if I go ahead and draw my energy diagram, I have my carbon here with our S and then our 3 P's. So P, P, and P. So I say, okay, here is our 2 P's here. So what's going to happen here is that this carbon is not going to be sp3. And the reason for that is because of this double bond. So if I go ahead and instead draw something called sp2, what I'll see here is I'll have sp2, 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 and then a leftover p. So the way that you can think about it is that p orbitals, they will participate in pi orbitals. P and pi, it kind of makes sense like that. And if you remember what I said earlier, double and triple bonds will be pi orbitals. So instead of having the electron from the carbon participating in an sp2 orbital to make a single bond, instead it will participate in the p orbital to make a double bond. So what you will see here is that all the single bond electrons will be here, and then our double bond electron will be right here, where here's a hydrogen, here's one of the oxygens, and then here is the second oxygen. This can be a little bit confusing, but the way that I like to remember it is I count the number of electron groups we have, not electron bonds, but electron groups. So in this case, we have 1, 2, 3 electron groups total. So sp2, that's going to be 1s plus 2p. In total, that's going to be 3. So sp2 will be associated with 3 electron groups. This will also occur when we see something like carbon with 3 bonds and no lone pairs. So what's going to occur here is that instead of having any pi orbitals, instead of having any p orbitals, it's just going to have an empty p orbital right here. And so as a result, all of these are now filled up by our hydrogen bonds. Honestly, hybrid orbitals are a very, very confusing topic, but once you get the hang of it, it should be a little bit easier to identify our orbitals. So let's take our example from before. If we were to be asked what orbitals make up this bond, you would say, oops, sorry, drew one too many hydrogens there. We would say, okay, so this is going to be an CsP2 and a hydrogen 1s. Okay. However, if we look right here with this double bond, this could either be CsP2 or Cp. This would be for the double bond, this would be for the single bond. Now, what about this oxygen? So now we're going to get into more complicated stuff, but for organic chemistry, mostly it will be focused on the carbon hybrid orbitals, and they will be more important a little bit later. I keep saying that, but trust me. So let's say that we have oxygen. So we have S, and we have P, and we have P, and we have P. In its normal state, oxygen will have 1, 2, 3, 4, 5, 6. So the idea here is that let's say that we have our hydrogen here and our hydrogen here, lone pair right here, lone pair right here. Great. So the idea here is that when we go ahead and this oxygen says, oh, I want to make an sp3 orbital, sp3, 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 what's going to happen here is two of those sp3s will be filled in by its own electrons. And then we have these two here making the bonds with our hydrogens. You may be wondering, okay, but why don't we make these into p orbitals? Why aren't these oxygens in, or why aren't these electrons in p orbitals? Well, the reason for that has to do with like VSEPR and energy theory. That's not how you spell VSEPR. VSEPR, I don't know how you spell VSEPR, I forget. Energy theory and all that stuff. But the general idea is that our bonds, they want to bring the overall energy state down. They want to be more stable. So if they have to bring other stuff slightly up from S to make things overall more stable, then it's going to be okay. But what you'll see here is that overall, we brought the energy levels down because while the S energy levels went up and therefore became more unstable, we brought 3 whole p orbitals down in energy. And as a result, the sp3 orbital is going to be more, more favorable. So what we'll see here is our same electron group stuff happening. This oxygen has 4 electron groups. sp3 is 1s plus 3p. That's going to be 4 electron groups. So this orbital stuff can be really, really confusing, but I hope that these little tricks here have sort of helped you understand how they may work in practice. So let's look at that example that I saw that I drew earlier. So if I go here and I say I have a carbon double bonded to an oxygen here and then 2 hydrogens right here, and this oxygen goes ahead and has its 2 remaining electrons here, this carbon would be carbon sp2 as we discussed earlier, and this oxygen would be oxygen sp2. And the reason for that is it has 3 electron groups and then 1 double bond. And because double bonds are the result of overlap of p orbitals, the double bond here will be carbon p orbital overlapping with the oxygen p orbital, whereas the single bond, the sigma bond, will be carbon sp2 and oxygen sp2. So it just depends on how you're looking at the molecule, what you're being asked for. Again, hybridization is very, very important, and although I would love to go over the whole theory and everything about it, I think that might make this video a little longer than it already is. So let's talk about one last thing. We're almost done, I promise. So let's talk about how hybridized orbitals can help us predict the structure of a molecule in 3 dimensions. So sp3, sp2, sp. So let's take carbon, for example. A carbon that is sp3 will look like this. a carbon that is sp2 will look like this. And I'm just going to use the carbocation example here. And then a carbon that is sp will look like this. So I'm using just carbon over here as a sort of placeholder, but this is the carbon that we're looking at. I will actually highlight each carbon that we're looking at in red to make it a little bit more obvious. So here's our carbon, here's our carbon, here's our carbon. So if we look at our sp3 carbon, we can say, okay, there are 4 electron groups around that carbon. There are 4 electron groups vying for space. If you follow VSEPR theory, this will be tetrahedral and 109.5 degrees. And the reason for this, that is not a 0.5 degrees. The reason for that is that electrons, things that are of the same charge, don't really want to be super near each other. And so each one of these geometries that we will discuss will sort of give us a maximization of the space between each of these electron groups, and as a result will make the molecule as stable as possible. So if you think about sp2 with 3 electron groups, that is going to be trigonal planar, because the best way to separate 3 groups is to make it into a triangle. And so then this will be 90 degrees. Sorry, not 90 degrees. I was thinking of a square. It's going to be 120 degrees, sorry. And finally, if we look at SP, what we'll see here is that it's just going to be a line, and as a result, we're going to call this linear planar, and it's going to have an angle difference of 180. So what we'll see here is that by figuring out our hybridization, by figuring out how many electron groups that these single bonds compose of in our hybrid orbitals, that can help us predict the overall structure of our molecule. And what you'll see, one more thing, what you'll see here is that tetrahedral will generally be drawn in sort of this fashion. And the reason for this is because as much as organic chemists like to draw, sometimes drawing things in 3 dimensions can be really, really hard. So what we'll do is we will represent our 3-dimensionality using 2-dimensional structures. So for example, this solid wedge here, it is showing that something is coming out of the page towards us, and this dashed wedge is showing us that something is going into the page away from us. So this is sort of a way of showing this kind of tetrahedral structure, this 3-dimensional tetrahedral structure, in a much simpler and faster way to draw, which is very important on exams. So I hope that this whole session helped you understand Lewis structures, resonance, this hybridization a little bit better. Again, these are all very, very hard topics, so you guys are doing a great job doing your best learning all this stuff, and I'm glad you came to me for help. And yeah, I hope that you have a great day, and I hope this makes learning organic chemistry just that much easier.